this point, you should be enthusiastic about squeezing and think that it has already revolutionized metrology. In fact, it is not the case because squeezing is fragile and using it demands extraordinary technical efforts. It is thus only in very specific cases that squeezing is used, and we will see the best example in next section. But why is squeezing fragile? To make a long story short, squeezing is fragile because losses reduce the amount of squeezing, that is to say, the potential gain compared to the standard quantum limit. By losses, I mean absorption, or stray reflection on an interface, or a detector quantum efficiency less than 100%. All these losses can be modeled by a perfect beam splitter reflecting a fraction of the beam equivalent to the losses, and followed by a perfect detection of the squeezed quadrature. The beam reflected to channel 3 is associated to the undetected losses and will play no role. In contrast, we will see that the empty input channel 2 will play a role. To see how a squeeze state is modified by losses, we consider the squeeze state alpha r entering channel 1 of the beam splitter. Since channel 2 is empty, we indicate vacuum in that channel. We want to describe the situation in channel 4 as a function of the situation in the input space, so we express the annihilation operator A4 as a function of A1 and A2. The amplitude reflection coefficients R and T are taken real and positive. Since we have a squeeze state alpha r in channel 1, it is a good idea to express A1 as a function of the operator AR, of which alpha r is an eigenstate. We consider the case of alpha and r real and positive, which means that the squeezed quadrature is Q. To understand the point I want to make, you must now calculate the average value of Q4 and its standard deviation. You must first express A4 as a function of AR and AR dagger in channel 1 and calculate A4 plus A dagger 4. After a few lines of algebra, you will obtain that simple expression. Taking the average in alpha r times vacuum is trivial, and the result is what could be expected. The average value of the Q quadrature is reduced by the factor T compared to its value without losses. Let us now calculate the fluctuations in the quadrature Q4. To calculate the dispersion, one must, a priori, calculate the average of the square and subtract the square of the average. You can do the full calculation, but you can rather use the trick you should know now and identify the terms stemming from the commutators. You will then find two terms. One term results from AR times A dagger R, and the other one results from A2 times A dagger 2. This result is very important. It means that compared to what you would expect for a squeeze state with an amplitude T alpha, there is a supplementary term R squared. The dispersion on the Q quadrature is not reduced as much as it would be in the absence of losses because of the term R squared. Can you explain what is the origin of this R2 factor? Technically, you can say that this term derives from the commutator of A2 and A dagger 2. But remember that this commutator is associated with vacuum fluctuations. So one can say that the vacuum fluctuations entering via channel 2 are responsible for the extra fluctuations in Q4. In fact, remember that the beam splitter is a trick to represent any kind of loss. So one can say that any kind of loss between the source and the detection adds vacuum fluctuations, which reduces the benefit of squeezing. Suppressing all the losses, including the inefficiency of the detection, is a demanding challenge, which has been taken only in rare cases.